In this video, we're going to learn how to combine radical expressions. Now, properties of rational exponents are the same as normal exponents. If you had two terms with the same base being multiplied, you add their exponents. So in this case, 8 to the 1/3 times 8 to the 2/3 can be rewritten as 8 to the 1/3 plus 2/3. And 1/3 plus 2/3 is 1. So 8 to the first would just be 8. So that's one way you can simplify. Whenever you have a term raised to a power and then raised to another power, those powers combine by being multiplied. So if I have 5 to the 1/2 to the fourth, that's the same as saying 5 to the 1/2 times 4, which is 2. So you end up with 5 squared, which is 25. Whenever you have two terms being multiplied and their product is being raised to a power, that power can distribute to each factor of that product. So if I have 4 times 5 to the 1/2, that can be rewritten as 4 to the 1/2 times 5 to the 1/2. Now the 1/2 is a square root, so this could be rewritten as 2 times 5 to the 1/2, or 2 square roots of 5. When you have a negative exponent, that can move to the denominator, so the exponent becomes positive. So if I have 9 to the negative 1/2, that can be rewritten as 1 over 9 to the positive 1/2. So I have 1 over the square root of 9, which would be 1/3. When you divide two terms with the same base, you can subtract their exponents. So whenever you multiply, you add the exponents, but whenever you divide, you subtract. So if I have 7 to the 3/2 divided by 7 to the 1/2, that can be rewritten as 7 to the 3/2 minus 1/2, which is 3/2 minus 1/2 is 1. So you get 7 to the first, which is just 7. And lastly, just like when you have a product of two factors, when you have the quotient of two factors, you can distribute your power to each factor in that quotient. So you'll have a to the m over b to the m. So in this case, for 5/27 to the 1/3, you can distribute that 1/3 power to the 5 and the 27. And 27 is a perfect cube. So the cubed root of 27 is 3. So we have 5 to the 1/3 over 3, or the cube root of 5 over 3. Now let's try to apply this to some other situations. So oftentimes you'll probably be given the example in a radical form, but you'll notice that the indexes don't match. So initially, when you see this multiplication, you say you couldn't simplify. But if you were to rewrite this into an exponential form, which is 6 to the 1/4 for the fourth root of 6, times 6 to the 1/3, now they have the same base, I can use these exponent rules to add their powers. So this can be rewritten as 6 to the 1/4 plus 1/3, finding a common denominator between those two terms. We have 3/12 plus 4/12, giving me 6 to the 7/12. Or if you wanted to rewrite this into radical form, again, this would be the 12th root of 6 raised to the 7th power. Now, when you're dividing, same thing. Usually, you need the same index to be able to combine these two radicals, but rewriting this into exponential form, meaning x to the 3/4 divided by x to the 2/8 in the denominator, I can subtract their exponents, so x to the 3/4 minus 2/8. 2/8 can be simplified into 1/4. So we have x to the 3/4 minus 1/4, which gives me x to the 2/4 power, which, when simplified, leaves me with x to the 1/2 power, which is just the square root of x. So this complicated expression is actually just representative of the square root of x when simplified. Now, let's say you have the multiplication of two different factors, but also still being multiplied with those different indices in each radical. Well, the way you want to go about this is to rewrite it to be x to the 4th y all raised to the 1/2 power divided by x squared y to the 8th raised to the 1/4 power. And then you'll use the distributive exponent property where you have a product of two factors and the 1/2 can be put onto each of those factors. So you'll have x to the 4th times 1/2, which should be x squared, times y to the 1st times 1/2, which is y to the 1/2, divided by x to the 2nd times 1/4, which would be 1/2, so x to the 1/2, and y to the 8th times 1/4, which is y squared. And to combine these, I'm dividing, so I'm going to subtract their exponents. So you'll have x to the 2 minus 1/2 times y to the 1/2 minus 2, which will give me x to the 3/2 times y to the negative 3/2, which can be rewritten as x to the 3/2 divided by y to the 3/2. So now you've combined them. Next up, we have the 4th root of 18 times the square root of 12. So we have 18 to the 1/4 times 12 to the 1/2. Now you can't handle this one the same as you did before because these bases match. So that's why I could add their exponents, but 18 and 12 aren't the same number. So I actually have to use their prime factorizations in order to simplify. So 18 can be rewritten as 2 times 9, and 9 can be rewritten as 3 times 3. So 18 is the same as 2 times 3 squared, and 12 is the same as 2 times 6. 6 is 2 times 3. So 12 can be rewritten as 2 squared times 3. Writing it this way, I'll have 2 times 3 squared to the 1/4 power times 2 squared times 3 to the 1/2 power. And now if I distribute that exponent in like I did above, I'll get 2 to the 1/4 times 3 to the 1/2, because 2 times the 4th is a half, and then times 2 to the 1st power, because 2 times a half is 2, times 3 to the 1/2, and now I can combine the like bases. So 2 to the 4th times 2 to the 1st is 2 to the 5/4, and then 3 to the 1/2 times 3 to the 1/2 is 3 to the 1st. So now if I were to go simplify this, I had a 2 to the 1st, so I could rewrite this. Instead of writing that as 5/4, I could keep them separate and have 2 times 3 times 2 to the 1/4 power, which gives me 6 4th roots of 2 to simplify. So when these two multiply together, it gives me 6 4th roots of 2. Now, one thing I want to go back to and talk about is this problem right here. If I were to write this into a radical form, and I'm going to put it in red to show you how to simplify this further, because it's the only answer I didn't put back into radical form that you see here. One thing I can do to simplify this further is when it's in radical form, which is the square root of x cubed over the square root of y cubed, I do have an x that can come out and a y that can come out, leaving me with x square roots of x over y square roots of y. And if I were to rationalize the denominator and get rid of that square root, I would multiply the numerator and denominator by the square root of y, which gives me x square roots of xy over y squared. That would be y times the square root of y times the square root of y, which gives another y. So y squared. So oftentimes, going back to your radical form, you'll be able to simplify further. And that is how you combine radical expressions.